So, hi everyone, I'm Mathieu Besancon, and today I wanted to talk to you about traits and lessons learned on traits for descriptions of graphs in LightGraphs. Right, so we're going to talk quickly about LightGraph for a quick refresher, then mention traits and what's this mechanism in Julia, and finally see the application to graph properties. So let's get to it. First, importing LightGraph just for quick visualizations, nothing important. And so, what is this package? So it aims at being a simple, fast, and extensible graph library in Julia. We'll mostly focus on the simple and extensible part. Simple here means that people should not think too much before importing LightGraph, because this is not bringing a whole ecosystem into the package. This is really bringing the minimum working toolkit for manipulating and thinking about graphs. And then if you want other functionalities, you can import additional packages around it. And since this is a fairly minimal package, you should be able to extend it quite easily. And so that's the extensible, and that's where the graph interface comes. So it's been fairly successful with more than 200 dependencies as of today in the general registry. So the graph interface, it's how do you reason about a graph generically, so without thinking of the underlying data structure, whether this data structure comes from LightGraph itself or from other packages defining new custom graph types. So there's basically an abstract type, abstract graph, and then a bunch of methods that you defined that help algorithms to reason on your graph. So if I define a new graph type G here, to be original in the name, I have to define a bunch of methods. So here, for example, I have to define an iterator which provides the edges of the graph, and then an iterator that provides the vertices of the graph, and then some other information such as the number of vertices, the number of edges, whether the graph is directed or not, being able to provide for a given vertex of the graph its outer and inner neighbors, and whether this graph has this given vertex or not, and finally whether the graph has an edge from the vertex I to vertex J, and that's it. That's all of the methods you have to define for a new graph type, and if you define these methods, you have a functional graph type that can be used by generic algorithms defined in LightGraph and outside of it. Right, so we have a simple abstraction, which is this supertype and a bunch of methods. Now, is it enough, and is it enough all the time? Sometimes we need additional properties, and especially sometimes we need additional properties to specialize some algorithms. So a way to do that is using this patch, and since you only know things about your generic graph type, either you define new methods or you add, for example, some type parameters to your abstract graph type. So for example, you could specify whether this graph type here has an integer, and which kind of integer is it storing vertices as, whether it's directed or not, whether it's mutable or not, and other things. And in the end, you would end up accumulating more and more properties into your abstract graph type. So this has several consequences. One of them is that to extend the information that are available at dispatch time for a graph, you need to PR on LightGraph itself, and LightGraph becomes a bottleneck for every developer. And also, you have more and more things to define for your graph, so you end up having more work to do when you define a new graph type, which is also a barrier for new people to develop custom graph types. Right, so instead of having this accumulation of new type parameters or new things to implement, one thing you can do is use traits. So we'll talk quickly about what this notion is. So a trait is a characterization of a type outside of the type hierarchy. So this can be a bit vague, but it's basically using dispatch to describe a given type. If I'm taking Linden's definition, a trait is a pure function of a type. Okay, so the pure function would be the characteristic you're trying to describe. The type would be the type you're describing, for which you're describing this characteristic, which returns a type value, and this type value is the one you dispatch on. So with this type value, you can dispatch on the appropriate algorithm, for example. Right, so I wanted to show a concrete example in outside of graphs to get something new. So here we will have always three different steps when working with traits. The first one would be defining the trait, so defining this characteristic. So here the trait would be mutability. So we are reasoning here not on mutability of graphs, but on mutability of integers. So you will have this characteristic mutability and then defining two other abstract types. I made them subtypes of mutability for documentation, but you don't even need that. And so immutable and mutable. Then the second part of the job will be implementing this trait for different types. So here for most integers, I will define mutability as returning the type immutable. And then for mutability, of big int, I will return mutable. So once I have this, I go on to the third phase, which is using my traits in a real situation. So here I'm defining an algorithm or a function, mySum, which takes some vector of element t, and then dispatches or calls to mySum of mutability of t. And then depending on the result of this will dispatch to either mySum of immutable with x's or mySum of mutable with x's. And then this will call some appropriate function, either the standard sum or some custom algorithm if I know that my element type is a mutable one. Okay. Right, so we have advantages to this situation here. The big one is, so we are defining new properties of integer types here, and we didn't need to rewrite Julia for this. So we can extend types that already exist, which is not the case with modifications of a type hierarchy. So once you define some types and they're supertypes, you cannot modify this anymore, and external libraries cannot modify this either. While you can define new traits and extend traits for types that already exist. And another nice one is that it's zero cost, because it's just dispatching on types and dispatching on properties of types that are defined only on the type themselves. And so this would be compiled away by Julia. Do we have drawbacks to this mechanism? Well, one of them is that we have a bit of a heavier syntax. Instead of having just mySum defined for each of your custom types, you have mySum, which has to call another mySum with the trait computed. And so this means that you have a second level of indirection instead of just having one level of dispatch depending on the value of your argument. So it can be a bit of a heavier signature and more methods to it. Right. And since you have a heavier syntax, several people have offered to automate this away. So you have more or less two generations of trait systems, traitor and simple traits that were there before, and traits and binary traits are the more recent ones. So let's get to the third part of the talk, which is application in LightGraphs. So LightGraph has been using simple traits for a while now, and so we'll see how it's using it for the directedness of a graph, which is the big use case it already had for traits. So again, we have the third phases of the trait of using a trait. First one is defining it with this trait def is directed. So we're defining a new trait is directed, which describes a given graph type. And then is directed is implemented by a function is directed, which takes this graph type. Then the second phase is defining this trait for types, and so we just do that by implementing this is directed function over a given graph type. And so here, for example, is directed of a simple graph is defined as false, while is directed of a simple digraph is defined as true. Right. And finally, the third phase is again using this trait in our algorithms afterward. And so here, instead of having these two levels of dispatch that we had for the integer example, we are using this trait fn function, which specifies that this will be a function that uses the trait system, and so it dispatches not only on a graph type, so here AG has to be an abstract graph, but it also dispatches with this special syntax on the directedness, and so on the not is directed of the graph. So here this function signature here will require an undirected graph, while the second one here will require a directed graph, and we see that with this 4 column and is directed. So it's a pure syntactic difference over the standard holy trace that we saw with the integer example. Right, so we saw how it was used for contiguous traits. Now, for directed graphs. Now let's move on to something else, contiguous vertices. To understand this, we need to go back to the context of LightGraph. And so it was done by first creating the essential data structures, so simple graph and simple digraphs, and then abstracting them away into an abstract graph. So the abstraction came after the data structure. And because of this, we have some properties of the initial data structures that are still there in the abstraction, so in the generic graph interface. And one of these properties is that integers and only integers can be used for describing vertices. If you have other properties, for example a name, so a string attached to each vertex, you would store this in external data structure, or in custom graph types. But the way you reason or the way the methods are reasoning on your vertices is with integers only. So for example, the has vertex is defined with this signature here. And so not only are vertices integers, but these integers are also used to index some vertex valued data. So if you have, for example, a floating point number attached to each vertex in some algorithm at some point, then the integer representing the vertex will also be used as an index into this vector. And so this means this integer is not only an identifier, an ID, it's also an index again. And so this is where this contiguity of vertices comes from. Since you are indexing into data structures with this ID of vertices, these need to be contiguous integers from 1 to the number of vertices, so without a hole or anything. So this seems fairly simple. This works fairly well because you don't need some external structure to keep track of which ID exists or not. You just have integers from 1 to n, let's say. And this is fairly practical, except in some cases, and we'll see one of them. So here, imagine I'm starting from a graph G, which is a complete graph. I remove 2 edges, and I end up with this one here. So some sort of square wheel graph, if you will, with 5 vertices, 3 in the center. And I will remove the vertex number 2, so this one in the corner. And now I end up with this new graph here. And now pop quiz, how do we know which previous vertex is now at which place? So we have 1, which I assume is still in place. What about 5? Did 5 become 2, or did 5 become 4, and so on? And this is fairly hard to keep track of, which is more or less okay in lots of cases. But in some algorithms, you are basically contracting vertices or merging vertices together all the time. And this can become tricky to keep track of which vertex is at each place, at each iteration of your algorithm. Right. And so this is problematic, and this can be seriously bothering for some algorithms. So how do you deal with that? Well, we had different solution candidates. The first one would be, well, you could just use metagraph here. So metagraph is a graph structure, so a graph type that can store metadata attached to vertices or to edges or to graphs themselves. So you could do that, but one problem is that you have then this metadata that would be your actual vertex ID, and then you have the vertex index, which is the one used in your algorithm. And so it means within the algorithm itself, you will not know you will not know your actual vertex ID because you're always reasoning on vertex indices. If you want generic algorithm at least. A second solution would be to create a custom graph type with maintained vertex ID, meaning if I remove vertex 2, vertex 5 will remain vertex 5. And this is basically what vertex safe graph is doing. But since a whole part of a code base was using this implicit assumption that vertex IDs were also vertex indices, then you had some parts of the code that was breaking in a non-deterministic way, or in a undocumented way at least. And so you had to have some specific cases to make the code break, and this was not in the signature or anything, and you didn't have any documentation on why would this break. And finally, so because of this, we could say, well, we could just drop the assumption of vertex contiguity. But some algorithms, well, not all algorithms need them, but some need this vertex contiguity property to work properly. And if you remove it, then you make these algorithms you make them slower because they need to keep track of vertices themselves. And so this means that you will make some algorithms pay the price for some of the graph types. And this means for the Lambda user that uses the generic graph types or the standard graph types, they will just get slower because you have some other corner cases that they will never hear of. And so this was not acceptable either. And so finally, we had this possibility of having contiguous vertices become a trait, so a characteristic of the graph type. And so this is the direction we wanted to push in. So let's dig in contiguous vertices as a trait. So this would mean the graph type themselves would indicate whether they are a contiguous vertex type of graph, and then algorithms will tag whether they need this contiguity assumption, or whether you have, for example, two methods, one for assuming the contiguity assumption and one that does not need this assumption. And thanks to this, you would not have additional costs for standard graph types because they would just dispatch to the most efficient method available, which assumes this contiguity. Right. So a first attempt was, as you can see, highly successful here. So we had two PRs, or I had two PRs with mutable traits and contiguous traits. And so some characteristics, I didn't want to use any external dependency, and I wanted to use vanilla traits to keep things as simple as possible and not add any wizardry to the existing code. So why did it fail? First reason was an increased complexity. So you have here a function which is cross-call minimum spanning tree, so computing something on a graph. And this was requiring, so it's a trait defense, so it's a trait function that required the graph to be not directed. And so that was the version before the PR, so you just had this function and it does stuff. And then after the PR, since this cross-call algorithm was requiring the graph to have this contiguity assumption, you have this first level here that requires the non-directedness, and then it calls cross-call MST with has contiguous vertices of AG, and then this. And so this dispatches to a second level of indirection, which is here, which is only valid for val true, which is the return type of this has contiguous vertices. So if has contiguous vertices is returning this val true, then this dispatches to this one, otherwise you get the method error, and so the effective function becomes this one here. And so you add a second level of indirection, it becomes more complex, and here you just have one path, which is the function only works for contiguous vertices and non-directed. Imagine if you have more combinations of the two traits together, this quickly becomes impossible to manage. And a second problem with this approach, or with traits in general, I'd say, is that traits helps to distinguish some behaviors and to tag some behavior or to indicate some behavior on some algorithms and on some types. And because of this will be touching a large part of your code base, and this is not just restricted to some new parts like you would have if you define a new type or if you define a new function. So to give you a more concrete idea, in LightGraph there is this experimental module that contains all the code, so all the new functions and types that we are not sure about yet, and that are not subject to semantic versioning. But for trait, this will not work because this is touching already existing code. This is redefining the signature and the type constraints on existing code. And so this can be a big worry because, well, if you try to follow semantic versioning, then you have to watch out that you're not breaking anything that already existed, even though you're restricting some methods, which can be problematic. Right, so we went on to a second attempt afterwards. One big motivation for it was, so vertex save graph was now used. So this is a package defining one vertex save type, and so this type was not assuming vertex contiguity, and this needed some way to reason about it in LightGraph itself. And so we had this has contiguous vertices. We had this current behavior that was implicitly assuming contiguity, that was not extensible, except if you rewrote all the algorithms in LightGraph, so you basically did not use LightGraph at all, or documentable, because this was to know if a given algorithm was assuming contiguity, you needed this to check the code itself, to dig directly inside the code and see if at some point you were using this assumption. So using vertex IDs as indices in some array, for example. So, and because of this motivation, we tried to redo these PRs and redo especially the contiguity PR. And so again, we have these 3 steps for traits, and the first one is defining the trait. So we have this new has contiguous vertices trait, defined by this has contiguous vertices function. So this time we use this the simple trait mechanism. And then just like is directed, we have this new function that returns true if a given graph type respects the assumption. And now, if we look at the new code for cross-call MST, so cross-call requires contiguous vertices and undirected graphs. And what we have in the signature is the where clause contains a subtype constraint. G has to be an abstract graph, but also after this semicolon, you have this special syntax thanks to the macro here. We can specify the given traits that have to be valid. So we have to have has contiguous vertices of G and also not is directed of G. And so these traits combine very naturally to define a method that is specialized for these 2 cases. Another positive side effect we had was that since we were explicitly marking this assumption that vertices had to be contiguous for a given graph type, then we could lighten some parts of the interfaces. So one example is the hasVertex function. If you know that your graph type has contiguous vertices, then you can define a default for your hasVertex function, which was not defined before. And thanks to this, we can reduce the size of the interface, so we can reduce the work done by developers which want to extend LightGraph with new types. Alright, and I'll leave you with one last, let's say, open question. What should we trait? Should we just describe every graph property with traits? And this could be an interesting thing to do. The two possibilities, the two, let's say, quick possibilities will be defining a trait for mutability of graphs. The hard thing here is which would be the default and which makes sense. And finally, we would also have a cheaply available property. So we could have a trait describing whether a property is cheaply available or not. So it's not. So we can always compute an adjacency matrix for a graph. The interesting thing for a trait would be to describe if this adjacency matrix is readily available. So it's just about providing a pointer, or if it needs some heavy computation, so iterating over the edges to construct the matrix. And so some generic algorithm could, thanks to this, use the trait, and if it's cheaply available, use the adjacency matrix. Otherwise, use some other mechanism to do something else, because we don't always need absolutely the adjacency matrix, but if we have it readily available, it might be easier. And we could extend this to almost traits. So traits that would provide you some information if cheaply available, or tell you not available, or force a computation if you need it. Right, and that's it for me. Thank you for your attention. I'll leave you with a few pointers here. You can check LightGraph and of course Lyndon's blog on traits. Thank you.